So now let's take a look at example number 6, which is again another example that we saw in section 5.2.1. We actually saw that this integral here was one of our really difficult integrals to tackle by setting up a limit with a giant sum. And the reason it was difficult is, again, you might recall, we didn't have any summation rules for how to deal with radicals. And so we kind of mentioned at the end of section 5.2.1 that this was too difficult to figure out, and this is why we went on the hunt to try to find easier ways to evaluate definite integrals. Well, notice that now we can use the fundamental theorem of calculus, part 2, to address this question very, very easily. And we'll start, of course, by noting that our function here is indeed continuous on the given interval. So I'll say here we see that f of x equals the square root of 2 minus x is continuous on the interval from -5 up to 1. Remember here that we're working with 2 minus x under the radical, so the largest value x could be is 2. If I go any larger than that, I start to get square roots of negatives. And so you might recall that this is going to be a picture that looks something like this. Over here at 2, I hit 0. And then I'm moving in a square root function fashion kind of backwards like this. And so the area that I'm looking for underneath my curve is this space here. Okay, well, now that I have a continuous function, I can state that by the fundamental theorem of calculus part 2, my integral from -5 to 1 of the square root of 2 minus x dx can be found very quickly as long as I can determine an antiderivative for this function. Oh boy, now this is a little bit tricky. I might have to experiment a little bit here. Maybe I could start by noting that if this was 2 minus x to the 3 halves power, if this was the antiderivative, then this would almost get me what I need. Notice that the derivative of this would allow me to take this 3 halves and bring it down to the front, and lowering the power by 1, I'd be down to a 1/2. So I would have 2 minus x to the 1/2 power. But I'd have a 3 halves in front, and the chain rule would also kick in and give me a -1. So I got to try to catch all of those extra pieces and address them. And so I'm going to attempt to do that with the following. How about this? Notice here if I took the derivative of this, I would be able to bring that 3 halves down to the front. I'd leave the inside alone and lower the power to a 1/2. And then I'd multiply by my derivative of the inside. And so my 3 halves and my 2/3 would cancel out. My negative and my -1 here would turn into a positive, and I would just be left with exactly what I started with. So again, remember that this is the way I can always check to see if I found an antiderivative that is correct. I can go ahead and just take the derivative and see if it returns me to where I started. Now, I can also see here that the most general antiderivative would again have a plus c on it. But with a fundamental theorem, all I really needed was to have any antiderivative. And so I'm going to choose to use the one that has plus 0 on it. Seems like an easy choice, because if I have a plus 0 on there, then nothing really changes. All right, so let's go ahead here and take a look at now the fact that I need to evaluate this from -5 to 1. So that means I'm going to do -2/3, 2 minus 1 to the 3 halves power, minus 2/3, 2 minus -5, or I'll write plus 5, to the 3 halves power. So really this is going to simplify here to -2/3 minus 2/3 times a 7 to the 3 halves. I don't really have too much of a way here to really kind of simplify this up or really make this any prettier. But I do need to note that I did make a small typo. Notice here that my antiderivative has a negative, so when I subtract that -2/3, this piece here is ultimately going to be positive. There we go. So again, there's not really much of a way that I can clean this up or make this look any prettier. This is my final answer. This is my exact area. And again, notice how easy ultimately that is, as opposed to trying to set up this big scary limit and calculate it. This is really showing the power of just how awesome it is to have this fundamental theorem of calculus part 2.